Hi, I am Marie-Noëlle Laurent, a painting conservator. I will discuss was carried out is conductor. I will discuss is conductor as part of my PhD studies at CISAG University and in the Institut National of Patrimoine. To correct the deformation caused by a tear in an easel paintings, the hypothesis that was emerged from practice has been to increase the rigidity of the canvas support by lining or by localized reinforcement to the back of the artwork. Although the Greenwich Conference in 1974 called for a moratorium of lining canvas, research has long maintained the idea of rigidity for correcting deformations. In recent years, research on the mechanical behavior on canvas lining and their long-term evolution has profoundly changed practices, emphasizing the preservation of the original integrity of the artwork and an increasing application of the principle of minimal interventions. In this approach, research carried out on tears since the 2000s has focused on the choice of adhesive and bonding type to allow the artwork to be tensioned without further reinforcement of the canvas supports. However, little attention has been paid to the issue of flatness and method of stabilizing the wall. The thread-by-thread mending is the answer to minimal intervention and avoids the risk of mechanical resurfacing of patches glued to the back of the canvas. This raises the question of how to maintain the flatness of a consolidated tear over time without lining or reinforcement, and how can flatness be restored using either rigidity or stress relaxation. These are the multi-parameters we wish to explore. Our research objective is to study the risk of deformation in a restored tear repair with thread-by-thread mending, with and without localized reinforcement, and to develop tools to understand the mechanical phenomenon involved. We aim to measure both the short and long-term loss of flatness and the distribution of mechanical stresses. Tear in an easel painting can be divided into two main groups. If the canvas is brittle or the fracture happens quickly, there will be little or no plastic deformation with jagged tear edge, broken threads, and short ends. If the canvas is not mechanically weakened and still offers some elasticity, or if the fracture occurs slowly, plastic deformation will occur, leaving the tear edge uneven with frayed and torn threads and irregular ends. These different types of fracture lead to two kinds of assembly. Butt joint, the threads face each other without a gap and can be glued in contact. And the lap joints, the overlap is more significant, allowing for shear hold. Three types of bonding are possible. Butt joints, the space between threads must be less than around 0.5 millimeters for this bonding to be possible. Overlap joint, the threads face each other but are frayed. The bonding does not occur on the single thread, but on each small fiber, with a larger overlapping area greater than 0.5 millimeters. In terminal joints, the threads are very frayed fried and can be interwoven. A scarf join, when the original thread is reinforced with an additional thread, is similar in nature. A fourth method, usually added in tear repair studies, is the boot joint with bridging threads. Thread 15 or 20 millimeters in length are glued on either side of the joint. In our study, this approach was considered as bonding with add reinforcement. A consensus has gradually emerged on the mechanical criteria for meeting the requirements of a tear repair. Reconstruction of canvas continuity to restore its mechanical integrity, uniform stress distribution, or at least as stable as original, sufficient tensile strength, prevention of tear propagation, preservation of the original flatness, and reinforcement of the weakened area. For all type of bonding, the first criteria is challenging to measure in the absence of mechanical data on the original canvas. Simple boot joint bonding meets criteria 1, 2, and 3, but not criteria 4 or 6. To meet criterion 5, preservation of the original flatness, in this case, the choice of adhesive appears as the only option. The adhesive must have a high modulus of elasticity with the risk of abrupt failure, which could be disastrous for the artwork. The addition of a reinforcement on the back third becomes essential. Bridging threads can meet criteria 1 to 4, but they might also meet criterion not 5 but 4, preservation. I did a mistake. Bridging threads can meet criteria 1 to 3, but they might also meet criterion 4 depending on the adhesive and methodology applied. Thread by thread mating of tear in its strict understanding of the bonding the facing threads one by one to reconstruct the wave has gradually emerged as an alternative to lining or patching. This choice considers that a solid connection of individual threads and properly executed will restore the mechanical strength and long-term stability of the artwork under tension. For this purpose, the chosen adhesive must meet several criteria. It must offer lower resistance than the canvas around the joint. The modulus of elasticity of the adhesive should be high enough for the canvas tension to remain below its elasticity. It must provide enough flexibility to prevent abrupt rupture under external stress. It should exhibit minimal creep. Good wetting properties, easy to apply and fast drying. It must be as reversible as possible and not compromise future treatments. In studies of adhesive choice, ultimate tensile strength, joint elasticity, and creep risk are the key criteria for selecting the most suitable adhesive. But the question of deformation and the search of flatness arise in different terms. Glass transition temperature, flexibility, and comparative rigidity between the original canvas and the bond are essential data to consider, which may contradict the expectation of an elastic joint that allows for slow fracture without risk of propagation. The first part of our experimental work involved building samples adapted to the subject of study and able to reply the question raised by our day-to-day practice as conservators. The choice of the study sample is essential. The quality of its fabrication and the critical evaluation of the shoe's parameters will determine the validity of the result obtained, and the number of samples will permit to reduce the error linked to the variation in implementation. Two study background canvas prepared about 30 years ago, showed significant reactivity on stone. In insufficient quantity, they served as a starting point for modeling our sample. We chose this criteria enable the setup of a deformation and reproducible tear, enable the study of deformation caused by various localized reinforcements, and avoid any filling and action on the paint layer. The selected sample follows the classic stratigraphy of an easel painting. A line in canvas, sized and print, covered with a thin layer of old paint and stretched on frame. A new uncoated manufacturer's canvas was used to obtain a standard canvas and ensure similar parameters. 5 canvases of different weight and textures were tested. Several tests were conducted with different concentration of sizing and priming, as well as various possible stratigraphy. Tears were made in both the warp and weft directions. Put joint tear by a simple scalpel cut from the back and the front. 5 tear tests were conducted on 2 canvases, number 13 and number 25. Deformation was observed after 2 days. Canvas number 27, fine but with relatively open weaving to permit thread by thread mending, was selected, and a simple and easy to implement methodology was developed to minimize variation related to implementation. Stretch on wooden frame of 40 on 40 centimeters using stapling by hand. This size is important for a sample that has to be reproduced many times, but it will allow positioning in the central area where tensions are the most homogeneous. Sizing with 10% skin glue applied with a brush on the stretched canvas and use the same adhesive for preparation based on calcium carbonate at a ratio of 9 parts glue to 9 parts filler, and glue and preparation around 40-45 degrees Celsius. The tear model is a butt joint tear made with a scalpel in the warp direction with a weft thread cut using a template. 15 samples were manufactured under a relative humidity of 50-55% and a temperature of 20-21 degrees Celsius. Since the first study conducted by Heiber, detailed research has been conducted on adhesive and bonding method used for tear repair through numerous tests and a statistical approach. These studies aim to create a framework for discussion through classification that help in protocol development. From the studies, we have selected 3 adhesives. The mixture of 20% sturgeon glue and 13 weight starch, which correspond to the classic thread-by-thread mending technique developed by Heiber. In her research, Anna Flock considers that this mixture is not suitable for butt joint because it's too heterogeneous and principally not ductile enough to achieve slow fracture within the joint. But the lower elasticity of this mixture can be beneficial for maintaining flatness, particularly when combined with a very thin reinforcement on the back of the canvas. Additionally, this method is widely used and offers true reversibility. So we have therefore selected it, adding a mixture of sturgeon glue and cellulose fiber, which provides more homogeneous and rigid joints with less risk of sudden rupture. The vinyl acetate ethyl emission Lineco with a neutral pH is the synthetic resin that studies have shown to be the most suitable and which we have therefore chosen. There are two systems for gluing reinforcement to the back of the work. Element glued, or sometimes sewn perpendicular to the tier, such as thread bridge or rigid rods gluing on a support, allowing stresses to be transferred. System of overlapping pieces, which increasing rigidity and decreasing size to increase the overall rigidity and attempt to maintain the alignment through stress transfer. We obtain the following sample tree. For our experimental methodology, 3D digital image correlation appeared the most suitable method. To observe and quantify deformation, it is essential to use a method capable of recording in plane and out of plane displacements and quantify them as a function of the stresses on the material. The IC3D meets this requirement. It's a non-contact technique that can provide a three-dimensional measurement of in-plane and out-plane deformations and displacements. In the 3D DIC method, for each state of an object, two images are simultaneously captured by two cameras looking at the object from slightly different angles. This correlation can be done relative to the first reference image or relative to the previous image in the form of incremental correlation. By using the image processing software Istracate from Dantec Dynamics. We use this one. With advancements in photographic sensor, this method allows observation of deformation over a very wide range of displacements, even for very small movements. The prerequisite for implementing the IC is the presence of a stochastic pattern suitable for image-to-image comparison. In the case of our samples, surface irregularities or the fabric structure are sufficient to obtain an image. So it's possible to track and visual displacement and deformations dynamically or statically, both in plane and out of plane. The measured displacement was compared to the precision level of the method. By correlating two images of the same object without any moves, the measurement is around 0.01 millimeters, as you can see on the right image, well below the displacement value measured on the sample. This measurement helps to determine the measurement limits of the expected displacement field and thus eliminate calculation inaccuracies. The stress related to the measurement deformation can be characterized from the stress-strain curve of the sample obtained through tensile tests. Since the tensile tests are performed uniaxially in the laboratory, the question arises of whether the curve obtained can be used to characterize the sample under biaxial tension. It's known that a canvas behaves anisotropically. In the case of a coating canvas, and for very small displacements, can the displacements caused by uniaxial tension be considered independent of the action exerted in the perpendicular direction? Samples with the same stratigraphy as the reference specimen were fried along the warp and weft in the upper and lower parts of sample. They were observed in tension in uniaxial tensile tester using dynamic 2D image correlation on the same software, Istra4D. To compare the stray fields in the central part of the specimen and in the upper and lower parts where tension is carried by thread in a single direction. Dynamic observation, that is continuous image capture, also will allow the observation of stress field evolution. Now we have established the methodology. Observation of tear and repairs will begin. 3 groups will be formed for each type of adhesive. Each group will be torn and observed in 3D DIC before and after joint bonding. The specimens will then be divided in 4 sets. One will remain without bond reinforcements, while the other 3 will be treated with the 3 selected types of reinforcements, bridging threads, metal rods, and rigid piece. You have to choose now which kind of glue and type of fabrics we are going to choose. Analysis of deformation and internal stress in 3D DIC will be performed at the time of bonding. The works will then be observed over the long term through controlled cycles of thermoeconometric variation. I would like to thank the Getty Center for organizing the international conference and for allowing me to present our research, and my supervisor and colleagues who helped me in this project. Thank you for your attention.
Please.
Hi.
Hi.
So I've used 2D DIC, but I've actually haven't been able to see 3D DIC in action. How do you have any experience? Did you have any beginning of results with some test samples with 3D DIC?
No.
And how is it harder than 2D DIC?
Actually, we have just seen the 50 samples in initial states, and they look. All of them are looking very in the same situation of the experimentation is we took a first image, and after we stretch a little bit the sample to have a displacement, and the displacement is not over 0.1 millimeters or 2 millimeters. And on the first image of 3D DIC in plane, we just see that the tension is very regular of all them 50 sample, of this 50 sample. We have not cut, or we are at the beginning and we have no other images.
Thank you.
Yeah, 25 years ago, Mary Piper Huff and I published a paper on using the dental wire for cupping and repairs, local repairs in contemporary paintings. And in that initial study, it was very clear that the viscoelastic behavior of the majority of commonly used adhesives, such as PVA, meant that any tendency for curl returned within a few days. The steel dental wire reinforcements were the most promising, and we were then worried about surfacing. So we looked and published at the Getty Yale conference on Canvas 20 years later. We went and looked at these samples we had prepared 20 years ago, and we had done with and without tension. So I would recommend to you, I didn't fully understand all of your experimental conditions, but the single most important condition to determine whether the repair will surface, in other words, project forwards, is whether or not the canvas was kept under tension for 20 years or under no tension, just barely kept flat by the keying out. So that condition is really important to look at in your studies, because that determines whether or not the rigid repairs will push forwards because of the break in the paint, which you can never reattach. The butt joint applies to the canvas. It would be nice to be able to butt joint the paint film, but it's not realistic.
Thank you for your comment.
Yeah.
No other questions. Thank you, Marie-Noëlle.